Hi everyone, this is the second video under complex numbers. So now we are at a point where we can we can define complex numbers. So what is the definition of a complex number? Complex number is a linear combination of a real number, and imaginary number, right? Real numbers and imaginary numbers. So this is the basic representation. Complex number is equal to real number plus an imaginary number. So we'll look into some examples. Now 3 plus 4i. We have 3 a real number and plus 4i, this one is, so here 3, this is real number, this one is called imaginary number. Right. So notice here that in the imaginary number you have a real number as well. Another one, 11 over 2 minus 13 by 4 times I. Now here what do you have? Now this is real number and here this is imaginary number. So what is the imaginary number here? So imaginary number here is, let me write down, the real number is 3 and imaginary number is 4i, pure imaginary number. Here the real number is 11 by 2 and the imaginary number is negative 13i by 4, because we have addition here, right, as a combination. This is how you combine, add, right? So I can write it like this, 11 by 12 plus minus 13 by 4 times I. Now it is apparent to you that the imaginary number is minus 13 over 4 times I, right? So this is a combination and this is called a complex number, right? So we can say that 3 plus 4i is an element of complex numbers, or this 11 by 12 minus 13i by 4 is an element of complex number, right? So you saw how you write real numbers as an element of the real set. Same thing can be used, set notation. Here this is an element of the complex numbers. So complex number encompasses all real numbers and imaginary numbers, and also combinations of both of them. So now let's try to represent a complex number. How do you represent a complex number? So in mathematics we use x and y to represent real variables, maybe independent or dependent, whatever it is. We use them to represent real variables, v, x, w, s, t, and all. Z, symbol z in complex numbers in general, under complex numbers we use symbol z to represent a complex variable. That means to represent complex numbers. So variables can take any values. So this complex number can take complex variable can take complex numbers, right? So in general we use z to represent a complex number, and this is how you represent it. And this representation, there are several representations. In your syllabus you will see only 2 representation, Cartesian representation, and there will be another one called polar representation of a complex number. But there's another representation which is called an exponential representation that is not included in your syllabus. So we will only learn about this Cartesian representation and polar representation of a complex number. So we will do most work with the Cartesian representation. So z, x plus yi, x here to represent the real number, yi to represent the imaginary number. Right? Notice here that y and x are real. Y and x are real numbers. Obviously y and x are real numbers. But this combination is a complex number. Now, when we sometimes we want to figure out what is the real number or what is the imaginary number of a complex number. Given a complex number, what is imaginary, what is real? So we use these symbols to get them. We have real part, right? Notice here that I didn't write real number, right? I wrote real part of C. In short, it is represented as RE of C. So real part of Z is actually the real number X. Given this complex number, this is called the real number. Now, when it comes to complex numbers, we define imaginary part, not the imaginary number. So here, imaginary number is y times I, but the imaginary part, because you know I is the basic unit. When you multiply I by another number, by a real number, you get an imaginary number. So you only need to know the multiple of I. That's what you are interested in. So they define imaginary part of C, Im of C. So imaginary part in this case is what is multiplying I. So what is multiplying I? Y is multiplying I. So this is the basic representation of complex number. So you should know the meaning behind RE of C and IM of C, because these have been used in your papers, right? Past papers. Okay, so we'll do some examples. Right. So find real and imaginary parts of the following numbers. So what is real? Real part. So real of this complex number. So notice here that it is named. It is not named, right? It is not given. It has not given a name, a variable. So it's just there as it is. So you put 2 plus 3. So what is the real part of this one? Real part of this one is 2. Imaginary part. Imaginary part of 2 plus 3i is 3. What is multiplying 3? Is the imaginary part. Now here this complex number is given a name W, right? So I can find what is the real part and imaginary part. Before that, I'm going to do this simple thing here. I'm going to write it as a combination, linear combination, plus minus p times I, right? Minus p times I. Can perfectly write this up. Now you can see what is the real part of C. Sorry, real part of W is A. Imaginary part of W is minus P. What is multiplying I? I is multiplied by negative P. So I write negative P. Right. So let's talk about equality. So what does it mean to say when two complex numbers are equal to each other? So we know when two real numbers are equal to each other, then for example, let's say x equal 9, which means x is equal to 9. X is equal to 9, right? So if you have x plus 2 equal 10, then x should be equal to 8. This is equality. So what does equality means when it comes to complex numbers? So if z sub 1 and z sub 2 are two complex numbers, z1 equals z2, z1 sub equals z sub 2 implies both ways. Real part of complex numbers, the two complex numbers are equal, and imaginary parts of two complex numbers are equal. This one here, this and is very important. Both must be satisfied, so that the both must be satisfied for the two complex numbers to be equal to each other. If either one of these is not satisfied, then two complex numbers are not equal, right? So please keep that in mind. So let's do some examples here. Samples. Suppose 2 plus 3i and 2 minus 3i. Let's check that these two complex numbers are equal. So what do we have to do? If two complex numbers are equal, their real parts and imaginary parts are equal to each other. So real part of 2 plus 3i is equal to 2, right? Which is actually equal to the real part of 2 minus 3i, because the real part of 2 minus 3i is also 2. What about imaginary part? Imaginary part of 2 plus 3i is equal to 3, and imaginary part of 2 minus 3i is equal to minus 3. So this is not equal to imaginary part of 2 minus 3i, because imaginary part of 2 minus 3i is minus 3. Minus 3 is not equal to plus 3, which implies 2 plus 3i is not equal to 2 minus 3i. So notice here that for two complex numbers to be equal to each other, their real parts and imaginary parts must be equal to each other. Let's look at another. Right. So given z1 is equal to z2, z1 and z2 are complex numbers. We are only talking about complex numbers in this. So given this is equal to 0, if it is given that it's equal to 0, then you know that real parts are equal to each other and imaginary parts are equal to each other. C and C2 are given. Find x and y. So if C1 equal to Z2, Z1 equal to Z2 means real parts of Z1 must be equal to real part of Z2. So what is real part of Z1? This is just 5. Real part of Z2 is minus y. So y is negative 5. One answer. Okay. Then imaginary parts are also equal. Imaginary part of Z1 is x. Imaginary part of Z2 is 10. So x is equal to 10. Let's see how we use equality with respect to complex numbers. Right. It's very easy stuff. So an important result follows is that if c equals x plus yi, if this complex number is equal to 0, what does that imply? It implies that x is equal to 0 and y is equal to 0. Only if and only x is equal to 0 and y equal to 0, then the complex number is equal to 0. The complex number is 0. So we know how to represent 0, nothingness in complex scale. Nothingness in complex scale is just 0, right? Both real parts and imaginary parts are equal to 0. So x and y are, this is the real part, this is the imaginary part. This means that real part of z equal to 0 and imaginary part of z is equal to 0. For example, suppose that let's say x minus 5 plus y minus 10 times I equals 0. Example, what does that mean? The real part is equal to 0 and imaginary part must be equal to 0. That means x minus 5 equals 0 and y minus 10 equals 0. That gives us x equals 5, y equals 10. Okay. So you have to know how to utilize these properties of complex numbers. Right. So let's talk about another definition with respect to complex numbers. You know about vectors. Vectors has a direction and a magnitude. So magnitude of a vector is written as modulus of that vector. So modulus implies a certain magnitude, right? So we cannot use inequalities with complex numbers, right? So we can use inequalities with magnitudes or real numbers. Now this is not true. Suppose you wrote it like this. This is not true. You cannot use inequalities with complex numbers. You can only use equality with complex numbers. But you can use inequalities with magnitude of complex numbers, because a magnitude of a complex number is a real number. So this magnitude is called modulus. So we'll get to the graphical intuition behind the magnitude when we discuss polar representation of complex numbers. Until then, we'll stick to this one. This is called the modulus of a complex number. Modulus of a complex number implies its magnitude, right? It's the magnitude of the complex numbers. How do you define it? Given a complex number x plus yi, where x, y are real numbers, it's very important to write this. Modulus of c, symbolically we represent like this: z, modulus of c, right? Modulus of z is the square root of real part square plus imaginary part square. So I can also write it like this: real part of c whole thing squared plus imaginary part of c whole thing squared. So square root of the sum of the two squares. This is called the modulus of C. So let's look at some examples. It's very easy to calculate this. Examples. Suppose C is equal to 3 plus 4i. What is the modulus? Modulus of C is written in this way. Modulus of C is square root of 3 square plus 4 square, which is square root of 25, which is equal to 5. Right? C equal to 5. Let's look at another one. Suppose W is equal to 8 minus 6i. 8 minus 6i. Then modulus of W is square root of 8 squared plus, you can put minus 6 squared, but it doesn't make any, it doesn't make any difference there. So you can just put 6 squared. That's 6 squared. So we have square root of 100. Square root of 100 is 10. You can see modulus of C is 5. Modulus of W is 10. Now we can say modulus of C is less than modulus of W. Notice here I use modulus with the complex numbers. Otherwise it won't make any sense. So if you want to comparison, right? Comparison means when you compare two quantities when it comes to mathematics, it usually refers to their magnitudes, right? Comparison with respect to their magnitudes. So magnitude wise, modulus of C is less than modulus of W, but Z less than W, no, doesn't make any sense. So never write that down, but this works with modulus, right? So let's look at another definition. Conjugate of complex numbers. So you have heard this word conjugate before, right? Especially when it comes to limits, right? When you're dealing with limits, or if you want to get rid of square roots, right? Not square root, like this, or something like this, or like this. All you do is multiply this by its conjugate. So conjugate refers to some, something of the same kind but a bit different, right? It's like a mirror world, something in the mirror world. So if you know about matters and antimatters, you know what happens when you combine matter and antimatter. So antimatter is based on the matter. It's a mirror symmetry of matter, right? Just like with that, for complex numbers, it has a twin. Their magnitudes are the same, actually magnitudes are the same, but they are two different things, right? Two different. They looks like the same, but there's a difference. Let's get to it. So given Z equals x plus yi, where x and y are real numbers, conjugate of C. So when we say Z bar, it's not zebra, it's Z bar. You have a bar on top. So Z bar, whenever you see this, that means conjugate of Z. So what is this? This is conjugate of W, conjugate of V, right? So you should learn to read this. Conjugate of C is obtained by reverting the sign of the imaginary number. You can see x is there, nothing changes to the real part. Just change the sign. If it is positive, you put negative yi. You put negative yi. That's it. That is the conjugate. That is the definition. It's very easy. So let's look into some examples. Right. Find the conjugates. Right. So we have 3 plus 4i. What is the conjugate? Conjugate of C is written like this, Z bar. Or you can write it like this, 4i bar. Okay. When you put bar, all you do is change the sign here of the imaginary number, nothing else, right? So imaginary number is 4i plus 4i, you change it to minus 4i. Right. Here, conjugate of complex number, minus 3 is the same, so minus 3 plus 4i, conjugate only changes the sign of the imaginary number, imaginary. part. This would be minus 3 minus 4i. So note here that the sign of real parts do not change. Sign of the real part do not change, but the sign of imaginary parts do change, right? Okay. So let me put a note here. Note, real part of C is equal to real part of conjugate of C. Real part of conjugate of C. And imaginary part of C is equal to negative imaginary part of C conjugate or conjugate of C. It's very important to know this. You can see here conjugate. What is the imaginary part of this number is 4. What is the imaginary part of this number? It's minus 4, right? So if we put 4 and here minus, it should be minus 4. So minus minus plus 4. So that's the equality here. So notice this with the conjugate. So we will use properties of conjugates and modulus later after we learn how to do arithmetic with complex numbers. So properties of these two, modulus and complex number, conjugates, will come in handy when we are doing more examples. Okay, so we have been building up to this point where we can use everything we learned up to now to employ in arithmetics of complex numbers. What are the operations we can do with complex numbers? Can we add them? Can we subtract them? Can we multiply them? Can we divide them? You know, with vectors, when it comes to vectors, we do the same thing. Can two vectors be added? Yes. Can two vectors be subtracted? Yes. Can we multiply a scalar, multiply a vector by a scalar? Yes, we can. Can we multiply two vectors? Yes, there are two ways to do that. One is called dot product and the other one is called cross product, right? Can we divide two vectors? No, we can't divide two vectors. We can divide a vector by a scalar, but we cannot divide a vector by another vector. So vector division is not defined, right? Doesn't make any sense. Then what about complex numbers? Can we do similar operations on complex numbers? Yes, we can do. So let's look at that. So maybe we'll do the proof of these arithmetics. No, we will do the proof here as well. Right, so first we'll start with addition, the basic operation. Let C1 equal x plus yi and Z2 equals a plus bi. This is just to make the distinction between two complex numbers. So we can work with any two complex numbers. Even if they equal, then that's fine. So I have to make sure to write this down. X, y, a and a, b, these are all real numbers. Right? So addition, how do you represent addition? Z1 plus C2, how do you do the addition? So you can use this. So x plus y I plus a plus bi. So I use brackets here to make the distinction. That's it. If you want, you can leave out the brackets. So here, if we have 10 apples, 2 oranges, then you have 2 apples and 5 oranges. So when you add them, what can you add? You can add apples to apples and oranges to oranges separately. So altogether we have 12 apples and plus 7 oranges. So don't write this down. This is just for illustration. Okay. So what does that mean? You can only add or subtract the same kinds, similar kinds. Just like human interact with humans. So here real number is x, here real number is a, so x plus a, then yi plus bi, I is common, factor it out and you get y plus b times I. Notice here that addition of a complex number gives you another complex number. This is an element of C. It's an element of C, complex number. This is a real number and this would be an imaginary number. Even if this is 0, you get a real number, but real number is actually a complex number, right? Real numbers are also included in the complex number. So we have this closure property as well. Closure is closed. You don't get beyond complex numbers when you have two complex numbers. So the real part of z1 plus z2 is x plus a, and imaginary part of c1 plus c2 is y plus b. Right? So if you are asked to take the conjugate, you should be able to take the conjugate. So let's look at the subtraction property. Right, so this is subtraction property, z1 minus z2, or you can have z2 minus z1, it's totally up to you. That means x plus yi minus a plus bi. So I can combine these two, x minus a, then y minus b, right, y minus b. Okay. Now notice here that this is also a complex number. So what is the real part of this? Real part of z1 minus z2 is x minus a. Real part of z1 minus imaginary part of c1 minus z2 is y minus b. Now we'll look into scalar multiplication. Right. So just like with scalar multiplication of vectors, we can define scalar multiplication of complex numbers. So let's take lambda being a real number. If you multiply z by lambda, this is the operation. So I can just multiply out lambda x plus lambda y times I. So notice here that this is also, again, this is a complex number. Right? So what is the real part of lambda z? Real part is lambda x. Imaginary part of lambda times c is lambda times y. This is the imaginary part of lambda times c. Now we'll see multiplication. Right, multiplication z1 into z2. That means x plus y I into a plus ib. So follow this order. First multiply out x into a, x by a, so xa. Then these two, x into ib. So that is xb times I. Then these two plus, we have plus here, plus plus plus, y times a is ya times I. Then these two, again plus plus is plus, yb, I into I is I squared, I squared. You know what I squared is? Now, xa, so write one step again, plus this one is xb plus ya times I. What about this one? This is minus I, so this would be minus 5b. So xa minus yb plus xb plus ya times I. That is our complex number. Again, notice here we get complex number. So if a question asks you to show that the given operation gives you a complex number, then you have to make sure that to represent the final result as a complex number, the general representation of complex number, real part plus imaginary parts. That's how you show. So real part would be xa minus yb is the real part, and imaginary part would be xb plus ya, xb plus ya. Right. So when it comes to product, notice here that you learned about conjugates. So what happens? What do you get when you multiply a complex number by its conjugate? Right. So note, suppose your complex number is this a plus bi. I'm going to multiply this by its conjugate. So a minus bi. What do you get? A into a is a squared. A into minus bi, minus AB times I. BI into A plus ABI. B into minus BI into minus BI, it's just minus B squared I squared. So what do you get here? These two cancels out. These two cancels out. And this one, I squared is negative 1. Negative 1 multiplied by this negative sign here, you get a positive 1, and finally you get A squared plus B squared. What is this? A squared plus B squared is a real number. This is a real number. Of course, this is a complex number. Yes, this is a complex number, but this is special. This is a complex number where this is pure real. In this complex number, this is pure real, right? Pure real number. This is very important when it comes to division. So next we'll look into division of two complex numbers. Right. So in previous 4 cases, addition, subtraction, scalar multiplication and multiplication, we were able to get our results that looks like a complex number. So final result would have a complex real part and an imaginary part. Now notice here, when it comes to division, you have a complex number in the denominator, right? Complex number in the denominator. We didn't have to deal with it up until now with the previous 4 parts. Now this is the first thing. First thing you do is to get rid of this complex number in the denominator. Now think about it. Pause for a moment and think, how can we get rid of these complex numbers? So if you do a certain operation, whatever you do, you know, if you multiply out by something, then you have to multiply the denominator and numerator by the same thing. If you divide, you do the same thing. If you add something, then you have to deduct the same thing, right? So you cannot change this quotient, but you have to do something so that this part here will become a real number. It will no longer be a complex number. So what can you do? Think about it. Right. So if you thought this through, then you will be probably right. To get rid of this complex number in the denominator, we saw just before when it comes to multiplication, and I put a note there. When you multiply a complex number by its conjugate, you get a real number. That's how you get rid of this imaginary number. So what I'm going to do here is I'm going to let's do one more step. I'm going to multiply both top and bottom by the conjugate of this number, not this number, conjugate of the denominator. So A minus BI, A minus BI. So whatever you do to the denominator has to be done to numerator as well. Right. So now what do you get? Here when you multiply these two, your answer would be A squared plus B squared. You learned this, right? A minute ago you learned this. So what do you get here? X into A is XA, X into minus, so minus XBI, then YAI plus YAI, then these two, minus YA, YBI squared. So you get A squared plus B squared. This would be plus XA plus YB, then plus YA minus XB times I. Still doesn't look like the Cartesian representation of a complex number. What I'm going to do is that I'm going to separate out. If I separate out, then XA plus YB over A squared plus B squared. This is one thing, and this is the real number, and YA minus XB over this is our imaginary number. This is our imaginary number. So I can write our real part of Z1 over Z2 is, real part of Z1 over Z2 is XA plus YB over A squared plus B squared. So this is imaginary part is ya minus xb over a square plus b square. You are not going to memorize any of this, okay? Not going to memorize any of this. Just learn the operation. This is what we do. When it comes to division only, we had to do this new thing. You just multiply both top and bottom by the conjugate of the denominator. Not the numerator, of the denominator. This one down here. That's it. Then you get this answer. Okay. So this is about it. Let's look at some properties of complex numbers, and then after that we'll do some examples. Right, so these are some well-known properties with regard to numbers. So real numbers have these properties: commutative property, associative property, distributive property. Also vectors also have these properties. So commutative properties, what does that mean? If you add C1 plus C2, oh, Z2 plus Z1, it's the same thing, it's equal. If you multiply out Z1 by Z2 or Z2 by Z1, it's the same thing. It's like 3 into 4 is equal to 4 into 3. 3 plus 4 is equal to 4 plus 3. This is called commutative property. Then associative property. If you have addition of 3 complex numbers, if you first add these two out and add that to Z3, you can do the same thing by adding Z2 and Z3 first, then adding Z1. So when you're multiplying out 3 complex numbers, you can associate Z2 and Z3 first, or can associate Z1 and Z2 first. That is called associative property. So simple things, right? You don't even need to learn these things. What about distributive? Same thing. Z1 into Z2 plus Z3, Z1 into Z2 plus then Z1 into Z3. If you add minus, it should be minus. That's it. This is the distributive property. So we looked into some of the basic operations that we can do with complex numbers, and we'll do some examples now.